In a game, a player throws a ball at a target. If they hit the target, they get 7 points. If they miss, 3 points are subtracted. Score begins at 0, and it's possible for a player to have a negative score. What is Shane's score after 6 throws if 4 are hits and 2 are misses? So for each hit, Shane gets 7 points, and then for each miss, you get negative 3 points, right? Because 3 points are subtracted. And when you do that math, it's 28 minus 6, which is 22. After exactly H hits and 6 misses, Susan scores 59. What is the value of H? So in this case, we have H, and each of those hits gets 7 points. And then 6 misses, and each of those misses gets negative 3. And then that is going to equal 59. So this is the equation you have to solve. And when you do, I'm sure you can do that. H will come out to be 11. And C, after exactly 20 throws, Suresh's score is greater than 85 and less than 105. If exactly M of these throws are misses, determine all possible values of the positive integer M. So the score is between 85 and 105, so that's the first established fact. And we know there's 20 throws, and we are told that M of those are misses. So M misses, and therefore the number of hits would be 20 minus M. Right? So then we go back to this, and let's just put it here, 85, and then we'll put 105, because we have to put a little bit of an equation in here. And that equation would be 7 for each of the hits, which is 20 minus M. And then for each of the misses, it's minus 3. Right? So then if we solve this, let's see here, what do we get? 140 minus 7M minus 3M. And then, let's see, 85 less than 140 minus 10M, I guess. And then, I guess we have to put everything on one side. So let's put the 140 on one side. So that will be minus 55, minus 10M, and minus 35. And then just flip it to get rid of the negatives. So this is going to be 10M. 55 and 35, and then divide through by 10 finally, and you get 5.5, and then M is going to be between that and 3.5. So since M is an integer, it could be 4 or 5. Identical rectangles, A, B, C, D, E, F, G, H, each with area 13. Area of the overlap region, EFCD is 5. What is the area of ABGH? All right. Okay, so the first thing, of course, is we have to try to see if we can split this into different categories. So I'm going to call that B. I'm going to call this B, A, B, and C, basically. So we are told that A, B, C, D, and E, F, E, G are 13 each. So basically what that means is A, B, C, D, A, B, C, D. So that means my A plus B is 13. And E, F, G, H would be B plus C. And that is also 13. Okay, so far so good. Doesn't really help, but let's see if that gets us anywhere. Anything else to give us? E, F, C, D. E, F, C, D. That's my B. That's 5. Oh, okay, then that makes it very easy then. Then you can just substitute it back into here. And that gives me A is 8, right? And if I substitute B equals 5 into there, I get C is 8. And then what are they asking for? A, B, G, H. So the whole thing. So the whole thing is A plus B plus C. Well, then that's pretty straightforward. That's just going to be 8 plus 5 plus 8. And that is 21. Moving right along, two identical right-angled triangles, JKL and MLK, overlap alongside KL, as shown. Sides JL and MK intersect at N. The area of the overlap region KLN is equal to half of the area of JKL. The area of the figure JKLMN is 48. If JK is 6, determine the length of KL. Okay. So JK is 6, so label that. And then I'm going to call these regions I'm going to label them A. And the reason I'm confident about that is the symmetry of the diagram, but also they say that KLN is half of JKL. So KLN is half of JKL. Yeah, KLN is half. Well, let's just write it out. KLN is, I've labeled it as A, and it's half of JKL, and JKL is 2A. So that's why I labeled it like that, just in case you're wondering. Okay, so then they tell me that the whole thing, JKLMN, the whole thing is 48. So that means 3A is 48. So that means A is 16. And then now I guess we just use the formula for a triangle to figure out KL. 1/2 base times height, so KL times the height, which is JK, would be equal to, I believe, 2A. Yeah. And that means that, let's see here, we need a little bit more space here. So 1/2 KL, that's what we're trying to figure out. JK is 6, and then 2A would be 32. So that means KL would be 32 divided by 3, I believe. And C, rectangle PQRS and triangle PQT overlap so that R is on QT. RS intersects PT and U as shown. The area of the rectangle PQRS is 108 and the area of PQT is 81. If the area of figure PQTUS is 117, determine the area of the overlap region PQRU. All right. Okay, so how do I do this? Let's see. PQT. Let's just write this out here. PQT, they're saying is 81, right? Okay. And then anything else? 1/2 base times height. So PQ times QT is really how you get 81. So that means PQ times QT, it would be 162. Yeah, and then PQTUS, the whole thing, PQTUS, the entire shape is 117. Okay. And there's one other piece of information they gave me, right? And that's that PQRS is 108. So PQRS, that's a rectangle. Okay, so that means that this guy here, this little triangle, that's going to be 117 minus 108. So that's 9, I believe. So let's just put that 9 in there. Yeah. And what do they want me to do? Figure out the area of the overlap. PQRU. PQRU. Okay. Well, that shouldn't be that hard now. Since, I'm just trying to see if I'm missing something. Well, I think that's it then. Then because PQT, they told me, right? PQT is 81. So this PQRU, this guy PQRU, that's just going to be PQT minus that URT. So that's going to be 81 minus 9, which is 72. I think that's it. If an integer n is written as a product of prime numbers, the product, known as its prime factorization, can be used to determine the number of prime factors of n. For example, the prime factorization of 28 is 2 times 2 times 7, which is 2 to the power of 2 times 7 to the power of 1. Positive factors of 28 are 28, 14, 7, 4, 2, and 1. Each positive factor includes 2, 1 or 0 2s, 1 or 0 7s, and no other prime numbers. Since there are 3 choices for each of the 2s and 2 choices for each of the 7s, there are 3 times 2, or which equals 6 positive factors of 28. How many positive factors of 675? Okay, so I'll explain this if the explanation they give didn't make sense. Let's say you have some number n, and you can break it up into its prime factors, p to the power of, let's say, a times q to the power of b. And I tell you, how many positive factors does this have? Well, it's simple. You just go a plus 1 times b plus 1. Got it? So I'll give you an example. Let's just use their example. Why not, right? So they gave 28 as this, right? So 28 is equal to 2 to the power of 2 times 7 to the power of 1. And if I said, how many positive factors does this have? Well, you take that 2, add 1, take this 1, add 1, and that's going to be 3 times 2, which is 6. And that's exactly what they got, right? So that's basically a neat little trick to do this quickly. So for 675, first step, of course, is to break it up into its prime factors. And I believe 675 is what? 5 times 5 times 3 times 3 times 3. So that's basically 3 to the power of 3 times 5 to the power of 2. So using that formula, the number of positive factors would be 3 plus 1, right? Take that 3, add 1. Take this 2, add 1. And that looks like 4 times 3, which is 12. So 12 positive factors for 675. A positive integer n has positive factors 9, 11, 15, 25, and exactly 14 other positive factors determine the value of n. Okay, so this one requires a little bit more thinking. So they're telling me that there are these and exactly 14 other. So a total of 1, 2, 3, 4 plus 14. So there's 18 total positive factors of this n. Okay, so that's the first piece of information. And then n, what does it equal? Well, n looks like it has these positive factors in there. So it's got to, obviously, those numbers have to be part of it. So 9 is basically 3 to the power of 2. 11 is a prime number. 15 is what? 3 to the power of 5. 3 times 5, I should say. And 25, well, that's 5 times 5. So all of these have to be incorporated into n. So I'm going to put in the 3. The 5, I'm going to put in, there's going to be at least 2, because there's 2 there, there's 2 here, so those got to go in there. And then 11 to the power of 1 so far. And then we have some other stuff that I don't know about. Yeah. Okay. And then, using our magical trick here, we can see so far how many do we have. That 2 plus 1, that 2 plus 1, and then this 1 plus 1. So that is what? 3 times 3 times 2, which is 18. Oh, so we already got 18. So that means this stuff here is nothing. Meaning, I don't need to add additional. So my n is just this guy right here. This guy right here. And when you multiply that all out, it's what? 9 times 25 times 11, which is 2475. So that's my n. So as you can see, it just takes a little bit of fiddling around. Okay, and now we get to the part C. Determine the number of positive integers less than 500 that have a positive, that have the positive factors 2 and 9 and exactly 10 other positive factors. Okay, so we have some n this time. I don't know what it is. And it has a positive factor of 2 and 9, which is 3 to the power of 2. And then a whole bunch of other stuff that I don't know yet. Okay. Oh boy. So where do I go from here? Well, I think there's going to be a few scenarios here. Let me just put that in the corner. There's going to be a few scenarios. So the first scenario is if n is just powers of 2 and powers of 3. That this whole stuff is nothing. And they're saying that's got to be less than 500. Okay. All right. And then how many was there again? These 2 and 10 others. So we got a total of 12 positive factors. Okay. So that means this a plus 1 times b plus 1 has got to equal 12. Okay. And then also, we have to keep in mind that A has got to be at least 1 and B has to be at least 2, since 9 and 2 are the part of the positive factors. So I think the only thing here is just to make a table. And let's see what I get. Okay. It shouldn't be that complicated or that time consuming is what I meant to say. So let's see what kind of parameters, because remember it's got to be less than 500, so we can't go on forever. All right, so let's start. A has got to be greater than or equal to 1, right? Okay. Let's make 1. If that is 1, then according to this equation, that's going to be 2 times something is 12, so 6. So B's got to be 5. So that means A plus 1 was 2 and B plus 1 was 6. And then therefore N, if you put those into here, and you can do the math, it's going to be 2 to the power of 1 times 3 to the power of 5, and that is 486. And that is indeed less than 500, so that works. That's a legit number for N. Okay, so similarly, we're going to go through a few more. If A is 2, let's see, this is going to be 3, so that's going to have to be 4, so therefore this is going to be 3. Yeah, and then therefore N would be 2 to the power 2 times 3 to the power 3, which is 108. Okay, so that works also because it's less than 500. Let's keep going here. If A is 3, then this will be 4, this will have to be 3, and then this will be 2. So I mean, N would be 2 to the power of 3, and then 3 to the power of 2, which is what, 72? Yeah, 72. So that works. And any more? How about A equals 4? If A equals 4, then this is 5, and then that's not going to work because that's not going to be able to give you a integer for B. If A is 5, this will be 6, this will be 2, but then this will be 1, but this is invalid because B has to be greater than 2, so I think I'm exhausted. So from here I got 3. Okay, so we got to keep going though, because this is not the only scenario, right? We can also have a scenario where N could be 2 to the power of something, like it's 2 to the power of 1 times 3 to the power of 2, but then another prime number, P to the power of A, let's say. That's another scenario of what N could be. Okay, all right. So where do I go from here? So I guess for this one I have to, same thing, I have to use the formula. So it would be 1 plus 1 times 2 plus 1 and then plus A plus 1, and that's got to equal my 12. So this means that A plus 1, this is 2 times 3, which is 6. So A plus 1, let's just put it in 2 times 3 times that. So A plus 1 would be 12 divided by 6, which is 2. So that means A is 1. That means this N is actually equal to 2 to the power of 1 times 3 to the power of 2 times some prime number to the power of 1, and that's less than 500. So that means this is 18p is less than 500. So I've got so P is got to be less than 27. So basically any prime number less than 27 would satisfy this, but we can't use 2 and 3 because those have already been used. So prime numbers less than 27, 5, 7, 11, 13, 17, 19, and 23. So that's what, 1, 2, 3, 4, 5, 6, 7. So I got 7 here. Okay. And I think that might be it, this 3 and the 7, but let me see if there's anything else. Another way would be if there's 2 primes that we have to add on. So instead of just P to the A, you have another prime Q to the B. Let's see what that gives me. That would mean that you have 1 plus 1 times 2 plus 1 times A plus 1 times B plus 1 is equal to 12. So that means that this is going to be a plus 1 times b plus 1 is equal to 2, right? But the minimum a can be is 1. So if a was 1, then that would mean that b would have to be 0. Oh, okay, so if b is 0, then this vanishes. So then we just get this again, which is exactly the same as what we did up here. So that means pretty much means that the only possibilities are this guy and this guy, which totals 10. So 10 is the total that we can get for this. Franco and Sarah play a game 4 times using the following rules. And you read all the rules. And then basically they give you an example, and then we start with the question. So I think it's easier for you to understand if I explain it with an example rather than going through the rules. Okay, so at the beginning of the first game, there are 40 beans in one jar and 0 beans in the other jar. After a total of 10 turns, 5 turns for Frank and Sarah each, what is the total number of beans left in the 2 jars? Okay, so let's start this off by talking about it with this example. Okay, so we start off with 2, I guess, jars or whatever they're calling it. And they are telling me that they've got some parameters here. They've got 40, right? 40 and 0. So there's 40 in this jar and 0 in this jar. Okay. All right. And then there's how many turns? There's 10 turns, so 5 turns for each. Okay. So let's go with that. So we have to put in 5 turns for each. So Frank's first turn, and then Sarah's first turn. Then Frank's second turn, then Sarah's, whatever their names are, second turn, and so on. Third turn, fourth turn, and finally the 5th turn. Now, the question tells you specifically that Frank removes in a very distinct pattern. He removes 1, and then 3, and then 4, and then 1, then 3, and then 4. So he always removes 1, then 3, then 4, then 1, then 3, and then 4, and so on. And you can see that here. Blah, 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 blah. Franco removes 1, and then 3, and then 4. So that's the pattern. And Sarah, her pattern is 2, and then 5. So we go back and we put that kind of pattern in here. So Sarah was 2 and then 5. So she removes 2, and then she removes 5. And then she removes 2, and then she removes 5. And then she removes 2, and so on. Got it? Okay, so now they're always removing it from this jar because this jar has nothing. So let's just put over here how many are remaining. And that's pretty much all that question is. So if there's 40 and Frank removed 1, there's 39. And then after removing 2, Sarah, 37, and then 34, and then 29, and then 25, and so on, right? You can count this down: 23, 22, 17, 14, and finally 12. So 12 is how many are remaining after those 10 turns. So as I said, I think an example explains this better than reading the question, because reading the question will mean essentially nothing. Okay, B. At the beginning of the second game, there are 384 beans in one jar and 0 beans in the other jar. The game ends with a winner after a total of exactly n turns. What is the value of n? All right. Okay, so we got to go through this whole thing now. Now, before we jump into this question, we should look at what we already did, right? Because this pattern just keeps on continuing. So let's type in, I think this should have been a 5 actually. Sorry about that. Hold on, F, S, F, S, F, S, F, S, F, S. That should have been an S5, this guy right here. Okay, so now we have F6, S6, F7, S7, 7. I'm just trying to see if there's any kind of a pattern. F8, S8, F9, S9, and okay, let's just see. So it's 1 3 4 1 3 4 1 3 4 for Franco, and then for Sarah was just 2 5, right? So 2 5 2 5 2 5 2 5 2 5. Is there any pattern? Does it ever repeat? 1 2 3 5 4 2 1 5 3 2 4 5 1 2 3 5. Yeah, right here, right here. You see, from here to here, right here, this journey here is the same as that. See, it's 1 2 3 5 4 2. This is 1 2 3 5 4 2. Okay, so that basically tells me that when you have these guys, it just keeps repeating. So how many moves is that? That's 12, right? Yeah. So let me just write it here. Every 12 moves, pattern repeats itself. Yeah, pattern repeats. Now, how many are removed in those 12? I guess you have to add up these guys. And when you do, I believe it's 37. 37 removed. Were they jelly beans or something? I even forgot what they are. Yeah, they're beans. They're beans of some sort. Okay. So now we get to the question. The question talks about 384 and 0. So this part is really what we're concentrating on. So every 12 turns, you're moving 37, right? So let's see here. How can I get close to 384? If I did 37 times 10, that'd be 370, and then plus 14 would be 384. So that means we got to go through this thing right here 10 times, and then another 14 beans. So that means 12 moves 10 times. So that's 120 moves. Yeah. And then when you get to 120 moves, we'll have 14 left. Okay, so that makes it a lot easier. Okay. So let's say we've already done 120 moves. And then we would get to the beginning of the 121st move, which I believe would be F61, right? And then S61. Because F60 and S60, 60 for each, add up to 120. And then let's just keep going here. F62, S62, F63, S63, and so on. So there was 14 remaining after 120 moves. So we'll put that in here, remaining. And now let's add in our moves. We know our moves, right? It's 1, 3, 5 for Franco. So 1, 3, 5, and then it's 2, 5 for Sarah. And let's see what happens. So after you remove 1, this will go down to 13. After you remove 2, this will go down to 11. This will go down to 8. This will go down to 3. And then, hold on. Let me do 1, 3, 4. 1, 3, 4. Sorry, this should have been a 4. And then at this point, Franco cannot remove 4 because there's only 3 left. So the game ends. Game ends here. So we could only go up until that point. So we went to this guy. So F62 and S62 were the last 2 moves. So each of them went 62 times. So 62 times 2 is 124. So that is the total number of moves. Part C says, at the beginning of the third game, there are 17 beans in one jar and 6 beans in the other jar. There is a winning strategy that one player can follow to guarantee that they are a winner. Determine which player has a winning strategy and describe this strategy. All right, so let's see what we can do. So we have the first jar, and we have a second jar, and this has 17 and this has 6, correct? Okay, so let's see here. Let's set this up. So we're going to have to do F1, S1, same big long song and then dance here. F3, S3, F4, S4, and so on, right? So let's see what happens. Okay, let's put in the standard stuff that they remove. For Frank, it was 1, 3, and 4, right? So 1, 3, and 4, and then it just repeats 1, 3, and 4. For Sarah, it's 2, 5. That keeps repeating. So 2, 5, 2, 5, like that. Okay, so now we got to figure out which jar that they remove it from. So that's going to help us figure out who can have a winning strategy here. Now, one thing is that the total number of beans at the very beginning is 17 and 6, so that's a total of 23, right? And at the end of these 4 moves here, we have removed 1, 2, 3, and 5, so that's what? We've removed 11. So this 23 is now 11. There's 11 remaining. So at this point, before we get to F3, we actually have a scenario where there's only 11 remaining. Now, how many are going to be in this jar and how many in this jar? That's going to vary, right? So, for example, you could have, let me hold on here. 1 plus 2 is 3. 3 plus 3 is 6. 6 plus 5 is 11. 11 was removed. So if 11 was removed, there should be 12 remaining. That's what I meant to write here. Okay, so if there's 12 remaining, we have to figure out how many are in here and how many are in here, right? So for example, there could have been a scenario of, like in this jar and then in this jar, how many, right? They could have been, say, 6 and 6. So you could have 6 in this jar and 6 in that jar. And what I can do is to put it here, 6 and 6. So at the beginning of, right before F3, you have 6 and 6, right? Because you have to have a total of 12. That's one scenario. You could also have 5 and 7. You could have 5 and 7. That's another way. See what I'm saying? Now, could you have 4 and 8? It's possible. I think 4 and 8 is also possible. And could you have 3 and 9? That one I don't think so. Because I think it's possible, but it won't help create a winning strategy. So let me summarize this. So these are some of the options, right? So let's just make this into a nice table. This one may not give us enough space. So we got Franco 3, S3, Franco 4, Sarah 4. And this was the 5th turn, 6th turn, 7th turn, and 8th turn, right? Okay, so let's create all the scenarios that we could have 6 and 6. We could have 5 and 5. 5 and 7. And we can have 4 and 8. And I think those are the scenarios that we need to create. Franco needs to create these scenarios in order to win. And at this point, the strategy is Franco needs to remove his beans from the fullest jar. From the fullest jar. To the jar that contains the most beans. Okay, so let's do this one here. This 6 and this 6. If there was 6 and 6. Well, they're equal, so it doesn't really matter what he does, which jar he removes them from. So if we're going to remove 4, 2, 1, right? So he removes 4, 2. It's 4, 1, and then it's 2 and 5. That's what they're removing. So once you remove it from the 6 and 6, we're going to have, let's say if he removes it from here, it'll be 2 and 6. And then Sarah, she could remove from either. Let's say she removes it from this first jar, it'll be 0 and 6. But then Frank has to follow this strategy here. Removes from the fullest, it'll be 5 and 0. Because he's removing 1, right? And then following the strategy, if he removes his 1 from the fullest jar, this would have gone down to... Okay, so now at this point, Sarah could remove 5 from this and bring this down to 0. And then that would basically mean that Frank had no choices, so Frank would lose. So that's a losing scenario for Frank. So we got to figure out a winning scenario for Frank or somebody. Now let's try this 6 scenario again, but let's see what we can do to make it possible for him to win. If he starts off by removing the first 4 from the other guy, or let's just say the same guy like this, so it becomes 2 and 6. And then Sarah then removes her 2 from the other one. So this remains at 2, but this jar goes down to 4. And then Frank, abiding by this strategy, removes his 1 from this, and that remains at 2. Now Sarah is stuck. She can't remove 5 because no jar has 5. So that means Sarah loses. So Sarah loses here. So that is a winning strategy, where by T7, the final numbers have got to be 2 and 3. Now let's see if there's any other scenarios. How about 5? This guy here, if we start off with 5 and 7, let's see what happens. If it's 5 and 7, if we start off and remove 4 from the fullest jar, right, because we got to abide by this, so that's going to be 5 and 3, right? And then Sarah, let's say she removes her 2 from this, so this will be 3 and 3. And then 1, it can be either since they're tied, so this is going to be 3 and 2. And then Sarah is going to lose because neither of them. So a 3-2 scenario, that's another scenario where the final jars have a 3-2 scenario or 2-3. It's interchangeable, right? So as you can see. Now let's try 5 and 7 again, because I think there's one more option. He's going to always choose from the fullest, so this will stay at 5, this will be at 3, but she could choose from here. So this will go down to 1, and this will remain at 5. He's going to bring this down to 1. He's going to bring it down by 1, and this will remain at 1, and then Sarah can't choose 5. So a 4-1 or a 1-4 scenario also looks like it works. So what that basically means is by T7, Frank has to force the jars to have either 2 and 3 or 1 and 4. You got it? Okay, let's try a couple more. Let's try 4. This one here, this 4 and 8, and let's see if the jars are at 4 and 8, if they can be forced into either a 2-4 or a 2-3 or a 1-4. Okay, so Frank was going to remove from this guy. Sarah could remove from either one, so let's try this one first. Then Frank's going to remove from here. And there you go. You got a 2-3 scenario. And then let's try another one. Let's say 2-8, 4-8, but this time slightly different. It's going to be 4 and 4 again, but Sarah could have removed from this one, but it's the same thing. Yeah. Is it the same thing? I think so. Well, this is 2, and then this is 4, and then 1, this would be 3 and 2. So it's just interchangeable. It's 3-2 instead of 2-3. So same thing. So that's basically the strategy to ensure that Frank wins. He's got to first force it down to one of these guys, either a 4-8 distribution like you had here, or a 5-7 distribution, or a 6-6, and then that's after the first 4 moves, and then by T7 he's got to force either a 2-3 or a 3-2 or a 4-1. See, these are 4-1s here. Yeah. At the beginning of the fourth game, there are 2,023 beans in one jar and 2,022 beans in the other jar. Determine which player has the winning strategy. All right, for this question, we basically have to do what we did in the previous question, but we have to extrapolate. So before we had, not as many, but now we have a whole bunch. Now, if you recall from previous questions, that every 12 turns, I think we were removing 37 beans were removed. If you remember, I think it was part A or part A, I think, of this question, that we kind of figured that out. Yeah. Or part B, I think. All right, so in any case, so that means we got to get sufficiently close to these numbers. So after some math, you can figure out that if you do 109 of those 12 turns, and each of those times is 37, it would be, let's see here, that's a total of 1308 turns, correct? And with all those turns, you're going to have 109 times 37 beans removed. So 4033 beans would be removed. Yeah. Now this 2023 plus 2025, that's a total of 4045, right? So if I remove that many, I'll have 4045 minus 4033, which is just 12. So that makes it much simpler. So basically what I'm saying is I've done this many turns and I've removed this many beans, and now I'm down to 12. Yeah. So we can basically bring this question to a scenario where how many turns? 1308 turns have done. So I can now start with the third 1309, 1310, and so on. I can kind of extrapolate and move ahead very quickly instead of doing it manually, which would take forever. Okay, now let's see what we have. So after 1308 turns, I've got 12 beans left. Now I've got to figure out what's the distribution, because I've got two jars. Remember, I've got jar 1 and jar 2, whatever, jar A, jar B, whatever you want to call them. Now, let's see here. I think winning strategies can happen, but let me just fill in the blanks here. Remember, who's going first here? It was a pattern, and so we're at F. F is at the beginning of the pattern. So this is going to be F, and this is going to be S, and then F, S, F, and S. And if you remember the numbers, it was 1, 3, 4, right? That was the pattern for F, 1, 3, 4, and then 2, 5 was the pattern for S in terms of how many is being removed. Okay, so after 12 turns, let's see here. So Sarah, I think Sarah, 12. So we have to fiddle around with this and see what kind of strategy can be done that's possible, first of all, and who will actually win. So let's just start with 12-0 and see what happens. So if we have 12 and 0 like that, then let's fiddle around with this. So if Frank removes 1, then let's say this goes down to 11 and then this remains at 0. Well, this is always going to remain at 0. This is going to go down to 9. Then this will be 6, and this will be 1. And this was always 0. And then Frank cannot remove 4, so that means Sarah wins. Okay, with the 12-0. Okay, great. Is there any other way? Let's try an 11 and 1 distribution. If there's an 11 and 1 distribution, Frank, he can bring this down to 10. This will be 1. This is going to be 8, 1, 5, 1, and then 0, 1, and then Frank can't go. So Sarah wins again. But the 11 to 1 distribution can also go in a slightly different way. This could be 11, this could be 0, and 9, 0, 6, 0, 1, 0. And then Frank loses, Sarah wins again. And I'm pretty sure that's it. So as you can see, if Sarah can force either was a 12-0 or 11-1 distribution, then she is guaranteed to win no matter what Frank does, no matter which jar he chooses the beans from. And that's possible. It's possible for her. These are possible scenarios. So yeah, that's a quick way of extrapolating using the fact that we have discovered that pattern. Then we can get it down to when there's only 12 beans left, and then the last 12 beans you can figure out this sort of strategy for Sarah.